I was young and foolish, or I should say more young and foolish than I still am today. Not quite this young though. 2 years ago I had just left the Recurse Center and I wanted to try out data science. And I had a background in physics and in programming, so I'd done some math and I had the technical skills to like give it a go. I did not have a very strong background in computer science. I'd taken one computer science course before and I had been a sysadmin in college, and that's it. And so this is great because it means that sometimes I'll learn things that is like blows my mind that other people take for granted because they learned it a long time ago. And this is one of those stories. So at that time I was looking around and like, okay, how do I do data science? I have no idea. And I met this guy named Max. Max was doing solo consulting. If you guys have read the OkCupid blog series, he was OkCupid's first data scientist, and he pulled a lot of the numbers that were in that blog series. So he was doing solo consulting and needed some help doing extra work he was bringing in, so I started working with him. And around this time in my life, I thought that books like this were super boring. I was like, you put data into a database, you get data out, like why don't you just talk about the details? And what I've learned since is that if a lot of smart people think something is interesting and I don't, that probably means I don't know enough about it yet. And that's definitely true for databases. So I was writing some Pigscripts for a client, and Pig is this very high-level language. You get to ignore all that like icky assembly and the hardware and the like bytecode. We don't need to worry about that stuff at all. Here's an example Pigscript, and so it's actually a pipeline. So we load up your data in the green over there. Trim off the columns you're interested in, so trimming off user ID and the website they visited in this particular example. And then you take trims and you group it by user ID and sort in relation groups. And then for each grouped item, you generate the user ID and then a count of how many different websites they visited. So this is a very trivial example of a pipeline. But this is what Pig looks like to write. And at the time I was using this tool called Mortar. And Mortar is great because you write one command, and then it spins up a Hadoop cluster for you in AWS, beeps and boops and does all your work for you, and then stores the output into S3. So it's awesome. You feel like a little bit of a wizard because you just push a button, and then this army of robots comes and does your work for you. So you get a lot of stuff for free. You get mapping and reducing, which is a data processing framework. You get HDFS to store all your bits and your bytes, and you get clusters and nodes. You get a cool query plan that makes stuff go super fast. And so I was feeling like Nikki right before everything went terribly wrong. And this was kind of my level of understanding of Pig when I started working with it. I was like, okay, I'm going to write the Pigscript, and then S3 has my stuff in it, and I can make graphs, right? That's really all I understood. And so I hit a bug one day, and it wasn't really like a mistake kind of a bug. It was more like this kind of a bug. I was doing something that I thought would be really fast, and it was really slow, and I had no idea why. I don't actually remember the specific thing I was trying to do. That's been lost to the sands of time. But I was probably doing something like this, where I was taking this huge data set and trying to trim it down so I could like develop quickly, and then run it down the whole thing. So I was probably doing something like, give me 500 rows that I care about. And so this was really slow. It's really crawling. And I was like, why is it so slow? I Googled around, I couldn't find any answers to this question that helped. And so I asked Max, and he said this. He said, well, seeking is slower than reading. And so I said, what? Because I didn't know what the hell I meant. And I've also since learned that confusion is a sign that you're about to learn something, that your mental model is either wrong it's a sign that your mental model is either wrong or is missing, in this case. And you're about to get it corrected for you. So we started talking about hard drives, which really surprised me. Did not expect the conversation to go in that direction because you have to ignore all that icky stuff, right? I actually like it, but I'm just calling it icky for dramatic effect. So we talked about what happens when most databases store information. So they do something like this, where they take each row, so this is a name, age, location, and they concatenate them all together. They magically turn it into binary, and then they write it on a disk that looks something like this. And then when you want to go retrieve that data off the disk, you have to have a little needle that goes in and finds it. And there are a few ways you can do this. One is reading. So reading is going and reading off a contiguous section of the disk into memory where you can then manipulate it really fast, which is great. There's also seeking, which is grabbing scattered sections of data around a disk because it's spread out. And so what he said was seeking is slower than reading. So basically what I was forcing my computers to do is jump around on this disk and find all the different bits of information. Because remember, I was asking it to do that. Give me 500 rows where the age meets a certain condition. So I was making it go 50, is that more than 15? Yes, okay, find 45, okay, is that more? Yes, okay, and I had to go and seek and find each age, each row. And that's why it was running so much slower than I expected. And so this sounds pretty straightforward, but it blew my mind. Because, remember, I'm writing this high-level Pigscript here, and I have to think about how a little metal needle in AWS's data center in Virginia is moving to write efficient scripts. I was like, what? So this is really cool. It's like you have to work at this level of abstraction and then like this one, right? And they actually connect, and I thought that was pretty rad. So this really changed how I looked at databases too, because this book suddenly started looking a lot more interesting, because there are all sorts of different ways you need to get data in and out of something, and different sorts of constraints that you might have. And do you guys know what those are?
Finches.
Finches, specifically Darwin's finches, right? This is the evolutionary revolution here. And basically, for all the different ways you might need to get data in and out of something, all these different types of databases just run up to fill those really specific needs. So you might not really want to commit to a particular schema or want to store documents, you might use Mongo. If you want to retrieve things really quickly, you can just index the crap out of everything and use Elasticsearch. If you want to keep history, you can use an append-only database like Datomic, which is, I'm pretty into Datomic. And if you want to do really fast analytics, you can use Redshift. And so let me tell you a little bit about why Redshift is so fast, because it has to do with that little metal needle. So it's not optimized to find user-level information quickly. You would not want to use this as a backend of a website, but if you want to make a copy of your database for your data team to play with, they'll be really happy with you. And here's why. Analytics needs a lot of aggregation. So you sum things, you average things, you count things, but across multiple rows, which sounds slow, right? Because that sounds like a lot of seeking, gosh darn it. But what if we move all those ages so they're next to each other on the disk, like this? Then to grab all those ages and check them all, we just have to go and read that little section in the middle. That sounds a lot faster, yay! So we've changed seeking to reading by doing this, and this has a fancy name. It's called columnar storage, which means storing the columns all together on disk. And Redshift does this by storing 1 megabyte of column data at a time in what's called a block. And this has a lot of benefits, one of which is that you can do compression, right? So if your age column's all integers, then you can do integer-specific compression on it and get a lot of speed benefits there too. But what's faster than reading and seeking? Ignoring data you don't need to read, right? So they don't actually do indexing in Redshift, but they do metadata. So each block, and I totally made up these numbers, each block has a metadata that says the minimum and maximum value for the column in that block. So block 1 has a minimum value of 1 and a maximum of 6, and so on and so forth. So if I need to find everyone whose age is more than 15, what do I need to do? Which blocks do I need to read? Just 3. I get to skip 1 and 2. That's awesome. That's so much faster than paying any attention to them. So skipping is really cool. Redshift has a lot more great stuff. There's nodes. You can run everything in parallel with that robot army I was talking about earlier. There are cool query plans that are based on the contents of your data. So if you change your data, the query plan changes, which is pretty cool. It's not even actually a database. I've been lying to you this whole time. It's actually a managed data warehouse service in the cloud. Kind of powerful and awesome. And it's so fast. So how fast, you might be saying to yourself? Well, I was a little lazy, so I found an example on the internet, but I'm sure it's fine. Of someone who had 21 million rows in their database in production. And they had it in Postgres, and they wanted to migrate to Redshift. So they just hit a button and transferred, copied into Redshift. And they ran a command and benchmarked it. So they did count star, which for all the non-data people in the room or non-SQL people is like, tell me how many rows I have. So the answer is 21 million. This took 10 minutes on Postgres to run. Guess how long it took in Redshift? Just pick a number. 2 seconds? I gave away the punchline. It took 1.5 seconds to run in Redshift. Like, no optimizations. There's all sorts of stuff you can do to make that even faster. That is 376 times faster just out of the box, which is pretty cool. But you know what's even more cool? 10,000 times faster. This is a crazy story. story, but I really like it. Max was the guy I mentioned earlier. He was doing some kind of a problem, and he was trying to do it in native Python. It was really slow. Like, it was going to take years to run, like really slow. And so he was like, aha, what if I use a matrix instead? And so he got 100x speed up from that. So he's doing matrix multiplication with really big matrices, which is very computation intensive. And then he was like, this is still pretty slow. And he found this library called OpenBLAS and used it instead of NumPy matrix multiplication. And BLAS stands for Basic Linear Algebra Subprograms. Linear algebra is a lot of matrix manipulation. And it is hand-tuned to the architecture of your computer to make it faster. So it runs different on different architectures. And it's from the 80s or 90s. It's like a very old library. And that got him a 10x speed up. And that comes with threading. So he got 10x from 10 different cores as well. And so he got a 10,000x speed up on his program from knowing about how the hardware works. And so this can really be pretty powerful depending on what you're trying to do. So in sum, Redshifts real fast. Hardware matters. The databases are really cool. Thank you.